In section 2.3, differentiation formulas, you get a chance to apply shortcuts when you want to calculate the derivative. A lot of you will find this section pleasing. It kind of reminds us of these step-by-step processes we took in algebra class. So it kind of gives you a nice way to calculate these derivatives without having to go through all of the complications of the limit definition. Now, the limit definition is wonderful, but as soon as the equations get a little more complicated, you found as you were working on your homework, you may have noticed the algebra got really complicated. So some of these shortcuts, just want to make sure they're great. We can use them, but just pay attention to any directions on quizzes or exams. If they specify you need to use the limit definition, then you must do that instead of using the shortcuts. But you can use the shortcuts to double check if you're right. So let's see how that goes. So the first thing we'll want to have you guys memorize is whenever we have to take the derivative of a constant. So sometimes I like to write the English right by the math. And anytime we take the derivative of the constant, we end up getting 0 back. So before I move on, I want to kind of combine these in one example. This is where we're going to take the derivative of a power function. And whenever you take the derivative of the power function, a cool pattern that happens is you are able to look at the exponent. And I like to think about this as a motion in a way. A little shortcut for myself is I take the exponent and I move it around to the front. So that's where the n is coming from. And that part gets multiplied by a new power function, but what it's done is it's dropped down the power by 1. So that's where we're getting the n minus 1 from. So if we were kind of looking at this in general, a lot of times you'll see the function itself, maybe off to the side. Here's in generic speak, y equals x to the n. Now, if we take the first derivative, we would notate this as y prime. What we can do is we take the n, we bring it around to the beginning of the function. We keep the base exactly the same, and then we would subtract 1 off of the power. So it's a little nicer when you see with concrete numbers. So we're going to demonstrate that right here. So looking at parts A, B, and C, we're going to look at calculating the derivative and kind of go with the notation based on the given function notation. So in part A, we want to find the derivative. So the first thing I'm going to write is f prime x. That's my notation to demonstrate. I'm looking for the derivative. And now when you look at what you're trying to take the derivative of, we see it's a constant. It's that pi. So because it's a constant, the answer would right away be 0. So nice, a little short. Moving on to part B, this is going to be demonstrating the property above, derivative of a power function. We are going to use the notation. So the original function y equals x to the 5th. We're going to use derivative notation y prime. And now if I'm going to do this, I'm going to take the 5, move it around to the front. So that's going to be 5. Keep the base the same, and we're going to subtract 1 off the power. So 5 minus 1. Now, when these are nice numbers, by the way, we don't have to do this intermediate step. We could just have gotten 5x to the 4th and be perfectly fine. That's how we want to be. But when you're first learning these things, sometimes it's really useful to show that intermediate step, just to help you get everything in line. Now it looks like we go from 0 to 100 from part B to part C. This doesn't quite look like any of the two above properties or shortcuts. So I have to kind of think back to my algebra class and kind of say, how could I get it to look like one of these? Right away, I'm going to rule out the derivative of a constant because I already see that there's a variable, 1 over square root of x. So this could be an application of finding the derivative of a power function in some manner, but we have to go back and think about rewriting. The square root always kind of comes up in my mind, or anytime I see a radical back from intermediate algebra, it has to do with rational exponents. So before we try to calculate the derivative, we're going to make sure we rewrite the function so that it's in a nice form we can then apply the property to. So I have not calculated the derivative yet, so I'm just recopying g of x over. And I'm thinking of square root of x. The next thing I would look at is maybe saying, instead of saying square root of x, that's x to the 1/2 power. And so that's kind of getting a little closer to the property above, or the shortcut above. But in order for me to apply this property, I need to make sure that I don't have any fractions going on. So one more algebra thing from our past, we end up having to rewrite whenever you see powers in the denominator, you can rewrite using negative exponents. So I'm going to look at this as x to the negative 1/2 power. So that's my biggest piece of advice. Always try to clearly rewrite the function that you see so that it's a power function. And then now would be a good time to take the derivative. So if I'm going to take the derivative, just remember, I'm going to use the appropriate notation. I'm taking g prime x. And the way I'm looking at this, I'm going to take the exponent. I'm going to move it around to the front. So that's negative 1/2. That gets multiplied by the original base, that's x. And this would be a case of why we like to write things out, because what we're looking at is taking the original negative 1/2 and we are subtracting off 1 based on the property above. So what we're kind of looking at this point is you're going to have to go through and simplify. It's not as nice integers, but we have to deal with combining over common denominator with those exponents. So I can rewrite this. I have negative 1/2 x, and negative 1/2 minus 1, that is negative 3/2. You can double check on the TI with the fraction key if you'd like. And for the most part, a lot of times, depending on the directions, we could leave it with a negative exponent if no one specifies it otherwise. But sometimes WebAssign or other teachers will always want you to rewrite it as a positive exponent. So at this point, you would maybe, this is kind of preferred, this is where we see the answers in the back of the book sometimes. We can rewrite x to the negative 3/2 as negative 1 over 2x to the positive 3/2. There's that exponent rule. Now, if we want to take this even further, I feel like that's pretty good, in my opinion, but sometimes we're really excited when we see that we have improper rational exponents. That's kind of a clue that if we were to convert it back to radical form, that we might have to simplify that radical. So there's a couple ways to play with it. If you think better in radicals, by all means, but you could take this a little further and rewrite it so you are back in radical notation. That would be x to the 3/2, so that's the square root of x cubed. If you prefer, you could always write the 2 in the index to help you. And then you could look at the square root of x cubed, and there's a little bit of simplifying going on. We would keep everything the same, but whenever we try to simplify the square root of x cubed, we would be able to pull out an x, and we'd be left with square root of x inside. So sometimes if it's beneficial, I'll make it a little prettier. Sometimes it's useful for us to simplify back to a square root, or if it started with a radical, maybe end with a radical. It kind of depends on where you're applying this derivative to. I kind of say if I don't have a calculator with me and I ended up having to plug in for the x's, it might be beneficial for me to change it back to a square root, because that's a little easier for me to work with if the numbers are okay. But if I'm just calculating derivatives for the heck of it as practice, I might just leave it in the rational exponent that I have above in blue. Just be careful, pay attention to what the directions want, and then you should be able to have that quite down for yourself. Okay, so we're going to build on this. Now remember, whenever we lecture, we start off with some of the concepts, and we assume you haven't had time to practice during the lecture, but usually when you start your homework, you'll be doing a lot of parts A, B, and C over and over again, and then they kind of build on that. So once we know these two properties, derivative of a constant is 0, and how to take the derivative of a power function, they're going to step it up just a little bit, and we just build on the previous concepts. And so if I'm looking at this next property, this is a derivative of a constant multiplied by a function. And so if I want to be really clear when I'm kind of thinking derivative of, remember it's a constant multiplied by a function. So not derivative of a constant, then times a function. You have this straight in the entire derivative. So it's really important to understand that, is this a constant multiplied by a function, or is, in the next few examples, is this a function multiplied by a function? So right now we have constants. If we're going to look at this, looking at part A, finding the derivative, I already see that I have my constant, -5, was getting multiplied by x squared. That's the function. So there's a couple ways to look at it, and then we could talk about shortcuts. What I'm looking for is, if I were to do this, they are saying you can pull the constant out in front of everyone. So that's the -5. Then that's multiplied by you taking the derivative of whatever the function was. So we can do that. We see we have this -5. If we take the derivative of x squared, what that ends up looking like, that's 2x. 2x to the power of 1, but a lot of times we don't write the 1. You can if you want, no one's gonna get mad. Or maybe web assign might, we'll see. So after we're done with taking the derivative of the function, the only thing we have to worry about is multiplying that 5. So -5 times 2, we end up getting -10x. There's our derivative. Now, a lot of times we do maybe 10 more of these or even 2 more of these, and we get kind of tired of writing this derivative notation. So it is quite okay to go with the shortcut and go straight to understanding that all we're doing is pulling the 2 out in front, or we can say -5 times 2 times x. So however you'd like to look at it, if you want to go straight to this step, a lot of times what I end up going with is I end up saying that it's -2 times 5 times x from there. See kind of my flow. But the reason is that we're looking at this property. So it's the same thing, nothing's different. But sometimes that intermediate step tends to be a little tedious, so that's why we kind of take that. Okay, so we'll step it on up a little bit more. What we end up having here is we actually have the derivative of a sum of two functions. Now, by the way, doesn't always have to be just sum. We could, well, we know that whenever you add and when you run into subtraction, subtraction is the same as adding the opposite. So technically what you could look at is if you have minus signs, it is possible to do this, apply the same property as well. So just want to make sure that you're clear. Sometimes you might write in difference. If I can fit that in. Whoops, I'm a little writing over my previous writing, but we'll see. So what this property is saying, and it's probably intuitive, you might be thinking, oh yeah, well, if we have two separate functions separated by a plus sign or a minus sign, if you want to take the derivative, you can just take the derivative of each piece. And the reason why these properties are holding, they actually relate to the limit properties back in 1.6. Remember, if you're defining what a derivative is, it's the limit definition as the h approaches 0 of the difference quotient. So if something works for how limits work, derivatives kind of take the same properties. So if we had a limit of the sum, we would take the individual, excuse me, I'm getting tongue-tied here, the sum of the individual limits. So if we have a derivative of the sum, we will take the sum of the individual derivatives. So if I were doing this and I'm trying to demonstrate this, I would say, well, I have d over dx derivative of the first function plus the derivative of the second function. And so then we would just calculate the derivatives using the properties that we already know and love or have been practicing. So this will be 3x squared, and then don't forget the plus sign. Derivative of x squared is 2x. And so now we have the derivative of the sum. And you'll also start doing a lot of these and you'll notice, oh, maybe I can skip rewriting the derivative notation. And yeah, that's not a problem as long as you understand what's going on. But a lot of times whenever you get lost, sometimes it really helps to really designate like, what was I supposed to be doing? So sometimes working backwards or writing out those extra mini steps tends to help us with the learning of this so it becomes more automatic. So we can step this up just a little bit. Maybe not just a little bit, maybe a lot. We're going to have ourselves a polynomial. And a polynomial, if you notice, it's the sum or difference of a lot of different terms. And all of those terms happen to be functions within themselves. So they're asking us, find the derivative of y with respect to x. We're using that notation. If your function y is equal to 3x to the fourth minus 2/3 x cubed plus x squared minus 5x plus 11, well, as long as we're noticing that we have a sum or difference, you could take the derivative of each individual term. So again, if I am denoting the derivative, I'm using what they're asking me to based on the function given. So I'm writing dy dx. And if I want to find the derivative of 3x to the fourth, I know that's 4 times 3x squared from, 3x to the third. I swear I can add and subtract. There we go. And I'll clean this up. I could do these mentally, but sometimes it really does help to show out a little work. Sometimes the major problems with calculus are all the little minor mistakes you make. So I recommend just taking it slow. So if I'm finding the derivative of the next term, I automatically put the minus sign in there so I don't have to worry about it. I would be looking at 3 times 2/3 x, this time x squared, taking off 1 from the power of 3. So it's dropping the power down by 1. Derivative of x squared, 2x. Now derivative of negative 5x. Now that's the case of a constant times a function, so you can pull out that negative 5. If you take the derivative of x, we should just have a 5. And I think you can, I know there's a property, it's a linear function. Let me see if I can explain it on the side. By the way, I'm stopping at this point because if I try to take the derivative of 11, that's a constant, so I would get a 0. If you'd like to write that when you are first starting, that's okay. But I'm kind of wondering if we take, just look at x for a second, just so that you understand where did I come from here? Excuse me, I'm going to write down on the 5. So how did I go from taking the derivative of negative 5x to get to negative 5? We can pull the 5 out, so let's kind of write it off to the side. We can pull the negative 5 out, but now we're taking the derivative with respect to x. Technically, we could call this a power function because it's technically x to the power of 1. So if you were to find the derivative, you pull the 1 out in front, you keep the x the same, but now you'd be subtracting 1 off the power. Now, if you do that, you end up getting x to the 0, and anything to the 0 power is 1. But don't forget, it was multiplied by a negative 5 everywhere else. So that's where they're getting this negative 5 from. Or one could say, if you have a term that's only, I should say, the x is the power of 1, it's a linear term, you can just take the coefficient as the derivative. We can kind of apply it back to maybe slope of a line. See how that works. Now let me clean this up. 4 times 3, we're going through some multiplication. So we have 12x cubed. And now if we do the multiplication of the fractions, we kind of got lucky. The 3's divided out. So we have minus 2x squared plus 2x minus 5. So that's the derivative of that given polynomial function. Okay, so the idea is get really good at going through the properties that we've just talked about. And once we're really good at this, we can then move on. We have now not just any property that's been boxed by our notes, but this property is so special, it has its own name. So I like to point out it's the product rule. But when you look at what you're taking the derivative of, you're taking the derivative of the product of 2 functions. That's kind of where we're seeing the dot. So kind of keep in mind that's a little different. And it's okay if you guys want to write out in English, derivative of a product of 2 functions. And the reason why I want to emphasize this is because a lot of times it gets confused with the property derivative of a constant multiplied by a function. So be careful. We know items are functions. Generally, you have a variable in them as opposed to just constant. So kind of keep your eye out for that. And what happens is it's got its own formula. And I'll let you guys think about ways you could help yourself remember them. I tend to write them out without the function notation, the f of x or g of x. So another way you could look at this, and sometimes it's easier on the eyes, we could say, write it maybe in red. Sometimes we look at these without the x's. And that's fg prime. And again, that's a product of 2 functions. So we can then say that's the same thing as G F prime plus F G prime. And sometimes you see this written a little bit differently in the textbooks or other items that you've seen before. Sometimes they'll start off with the other way around. It does mean the same thing, by the way, if you were to say, if you put the F first, this term first, and then we have this as well. We can play around with these. But I tend to not even go there. Oops, I was going to erase that and highlight that. Because you'll see in the next example, we have another rule. And if you kind of have the product rule memorized in this manner, it's going to help you a lot. So we'll inspect that in a little bit. So sometimes just saying it out loud, GF prime plus FG prime, or if you want to be really specific, we're looking at the derivative of a product of two functions is the second function times the derivative of the first plus the first function times the derivative of the second. So that's a lot of words for this notation. But the idea is when you look at what you're trying to take the derivative of, as I'm looking at example 4, I realize that there's a product right here. And when I look at, well, what are we taking the product of? Well, I look at the first part that has a variable in it. So for sure, we got a function. And the second part also has a variable in it. So we also have a function. So again, we have a function times a function. There's my abbreviation again, function times function. And when you run into that case, what you want to pay attention to is let's label who our F is and who our G is. And we do this with just understanding that whoever you see first is F, whoever you see second is G. So don't switch it around, just kind of keep that same sort of format. And we do know if we see it's a derivative of a product, you can go straight to writing out the generic formula, G F prime plus F G prime. And you kind of see I space it out a little bit because we need a little bit of space, you'll see. But just kind of keep in mind that there's product of these two individual terms. And what I like to do with these is I actually have to do a little side work. You get pretty good at it. You can go mentally, but remember we said everyone makes mistakes in calculus. It's because of the little stuff. So I prefer to kind of write out my thoughts and saying, okay, if I know F, and this will be my organized scratch work, F is 2x squared plus 3x minus 1. And then also G is 3x plus 2. So I write it off to the side. And then I calculate their corresponding derivatives. So that makes it a little nicer. So F prime, if we were going to calculate the derivative of 2x squared, that would be 4x. The derivative of 3x is just a 3. And then the derivative of -1 is 0. So we're good there. Then calculate the derivative of the second function. So that's G prime. So that's just a 3. So having an organized way to express who your derivatives of these individual functions were is very helpful, just in case you make minor mistakes in the algebra from the formula. So if we do this, I'm going to separate my problem out a bit. I'm going to plug in directly what we're looking at. We have G. So in our case, the G was 3x plus 2. The F prime is 4x plus 3. There is a plus sign from our original formula. Our F is 2x squared plus 3x minus 1. And then our G is 3. So even if you mess up along the way, if you kind of show that you're demonstrating this part correctly, there is chance of partial credit, I guess, if this is a handwritten assessment. Now, once we have that situated, what we can do is just simplify. We see a product of two binomials. So we can multiply those out if we'd like. So we have 3x times 4x is 12x squared. 3x times 3 is 9x. 2 times 4x, we have 8x. And then 2 times 3 is 6. And then that second part is distributing that 3. So it's kind of a backwards distribution, but that should give us 6x squared plus 9x minus 3. And once we multiply everyone out, we then go through and we just look for like terms. So I just scan each one and just careful. I'm saying, okay, do I have another 12x squared? And not another 12x squared, but I do have an x squared term. So 12x squared and 6x squared make 18x squared. Then I go through and say, okay, I have 9x, 8x, another 9x. So take a little time, just be careful. I believe that should be 26. So that's 26x. And then if I have any constants or like terms, I do. That's 6 and a negative 3 gives us a positive 3. So that is the derivative of the given product. Now, you know, to be honest, we really didn't have to use the product rule here. I was just flexing my mathematical muscles. We can actually approach this problem a little differently. We could maybe check this and say, well, let's look at it maybe by multiplying this product out, if it's easy to do so. I mean, I guess I say easy with a very light touch because not everything's easy, but easier. We could have taken this root. So if you feel confident with this, I'm going to rewrite the problem over again just so that we can see. And if we notice, all of these, we have a trinomial times a binomial. We could actually multiply them out, maybe before we even take the derivative. But if we do that, we have to remember that we have to keep writing the derivative notation because we have not taken the derivative yet. So if I were to multiply this out, it's a distribution. We can play around with distributing the 3x times the 2x squared. That's 6x squared. 3x times 3x. We have, excuse me, not 6x squared. I'm just obsessed with the squares today, but if you multiply an x times an x squared, you should get an x cubed. 3x times 3x, 9x squared. And then 3x times 1 minus 3x. And then we do the same thing. Might have to open up my derivative notation to fit everyone in, but I just take the 2. 2 times 2x squared. We have ourselves a 4x squared. 2 times 3x is a 6x. And 2 times negative 1 gives us a negative 2. So, I mean, that's a lot of multiplication. I kind of use a lot of markings so I can keep my place. But it's about not too horrible to multiply out, I would say. So before I take the derivative, I want to see, do I have any like terms? By the way, I can start to use parentheses again because I haven't. There's no need to use brackets. And so I just combine my like terms. I should get 6x cubed plus 13x squared plus 3x minus 6. And then now the product of the two functions is now a polynomial. So now if we're going to take the derivative, you can take the derivative of individual terms. That will be 6 times 3, that's 18x squared. 2 times 13, that's 26 with an x, and then the derivative of 3x is 3. And then if you notice, we got the same thing that we had. So then the question is like, why care about the product rule if I can just multiply these functions out? And that's a great question. But remember, whenever you see the derivative of a product, sometimes these products won't be that nice to multiply out. I would say the product rule would be more useful when you see exponents on your binomials or trinomials. So just kind of a sneak preview. Maybe I believe it's 2.5. So little note, product rule is usually more useful in situations like functions for, oops, let's write this out. So what if I had something like, derivative with respect to x, and maybe I have something like 2x to the 4th minus 3x, but it's to the 8th power. And then that's multiplied by 7x minus 1, maybe to the 10th power. Well, my friends, that's going to be very painful to have to multiply out. But if we incorporate this along with the chain rule, you're like, what's such a chain rule? We're going to find out in 2.5. Taking the derivative of this expression is not too horrible. So we'll see how that works out. But like I said, the product rule, we will be using it. If you run into situations, again, you always want to take the easiest route that you feel most comfortable with, and that's fine as long as the directions don't specify any other method to take. But if they want you to specifically use the product rule, then you'd be forced to demonstrate it like the way we've done above right here. So just be careful. You know, when you think you're done with something, read the directions over again, and that usually kind of solves the problem. Did I do what I was supposed to do? Double checking all the math, etc. So we'll get back to chain rule, whatever that means. But before we do that, let's play along. I have one exciting problem. And of course, keep in mind before we jumped into product rule and quotient rule, we're getting really good at some of the individual properties. We probably practiced product rule a lot more until we get to quotient rule. Sometimes I'd like to throw in a little more complicated examples during my lecture so that when you run into them, you don't freak out. So here we have it. We have ourselves the quotient rule. And that is, I mean, now it's kind of more obvious to look at, but if I'm going to spell this out in English, this is the derivative of a quotient of two functions. So we have the function on top in the numerator, that's f, and the function on the bottom in the denominator, that's g. So if you're looking at the derivative of a quotient, we end up having a formula. And it is a little painful at first to memorize, but you end up using it so much, it ends up being second nature, kind of like the quadratic formula. So what we're going to look at is maybe kind of a nicer way to approach this. I know sometimes when I have the x's involved, it's a little noisy the way I look at it. So I might go and say, you know, same sort of thing I did with the product rule. I believe I was using, you know, what happens if you have f over g, derivative of a quotient, and that's prime. So I kind of play with it that way. And so if I take out the function notation part, the of x part, I notice in the denominator, I have the denominator function square. And then if we look at this, we have g f prime minus f g prime. that look familiar? Let me look at this one more time. G f prime minus f g prime. I've seen that before somewhere. Ah, look at that. G f prime f g prime. So in the product rule, it's kind of what we were trying to talk about. Keep in mind the product rule had a sum, but now in the quotient rule, we have ourselves a difference. So be very careful with these formulas. A lot of times if you're practicing them, I always recommend writing out the generic formula first and then going through everything and plugging the correct functions in. So I'm gonna apply the quotient rule to a problem we've kind of been working on throughout the first part of chapter 2. If we kind of talk about finding the equation of a tangent line one more time. So things don't change with the ability to find the equation of the tangent line. We still need the point of tangency. We still need the slope of the tangent. But in order to find the slope of the tangent, that's where most of our work comes in. So kind of write out what your thoughts are on the side. That's usually very helpful. So we're going to need two things. Maybe I'll write this out in purple. Remember, equations, we're going to need a point. Of the tangency, or of tangency. And in our case, sometimes they give you the point, but this time, I think it's like another example we had. We had 1, they're giving us the x value, but we need to figure out who the function is evaluated at 1. So we can do that. That's not a problem. Just say, well, that's the same thing. The function evaluated at 1, if we need to show a little work off to the side, f of 1, that's the square root of 1 over 1 plus 1 squared. A little bit of math magic, and you should get 1/2. So now we do have the point of tangency. And the other thing we need is the slope of the tangent line. So just remember what the slope of the tangent would be calculated by finding the derivative of the function, but then plugging in the x value for the point of the tangency. So before we do this, it's recommended we want to find f prime x first. So find the first derivative first. So if we go back to our function, we'll notice it's not a polynomial. We have ourselves a quotient of two functions. And so with the quotient of two functions, just remember that fraction bar kind of gives it away a bit, but label what you're thinking. The top, or the numerator, is always the first function, f. The denominator, the bottom part, is always the second function, g. So if you're going to calculate the derivative, let's write out the actual formula. We maybe need a little bit more room on this paper, we'll see. So we'll start off. I'm going to use that notation, f prime x, according to my function. Now remember, we're looking at g f prime minus f g prime over g squared. Practice that a lot. And before we can do anything, it might be useful off to the side, a little scratch work, is show your work for who you named your f. So in our case, it was the square root of x. Who you named your g. In our case, it was 1 plus x squared. And then the calculation for your derivatives. So I'll do g first. That one's a little quicker for me. G prime. Derivative of 1 is 0. Derivative of x squared is 2x. Then we have that square root function. And a lot of times you do this so much, you start memorizing what it is. But just, you know, as you're going, you're learning. It helps if you want to rewrite it to the rational exponent part. That way, when you're finding the derivative, you know that it's a power function. Bring the 1/2 around in front. Then we're subtracting 1 off of the power. So we have 1/2 minus 1, a little bit of math. That becomes negative 1/2. And sometimes if you want to, kind of depends on what we're trying to do, you could rewrite the negative exponent as a positive exponent so that you're kind of switching the level. Or sometimes you could rewrite it back so that it is in square root radical notation. There's lots of different ways to play with this. My preference, if I know I'm going to be using this derivative to apply to a more complicated calculation, I might not even go towards making this a fraction again. So you may see me use this form. But of course, a lot of us think differently. We can play around, but I kind of recommend kind of keeping most fractions out of it. But then again, the more you explore, the more you learn what works for you. So having said that, if I'm going to plug this into my function or my derivative formula setup, I'm going to need a little bit more room. But let's start off with who g is. G is 1 plus x squared. Now that's where the f prime comes in to play. I'm going to use this version, 1/2 times x to the negative 1/2. Gotta be careful. Don't forget that 1/2 exponent. So that's g f prime. Now we want to subtract off. Don't forget that's coming from our formula, the f. So in our case, do we want to use the square root of x or the x to the 1/2? I might prefer, since I'm trying to be consistent, I might go with x to the 1/2 power. So that's multiplied by our g prime, which is 2x. That's not quite done yet. We still have to put this all over g squared. So remember, g was 1 plus x squared. And that is squared according to our formula. So be careful. It really helps to show exactly who your f, g, f prime, and g prime are, and then relate them back to the actual quotient formula or the quotient rule. That could get a lot of partial credit if this were a hand-graded test. At this point, this is where we would try to use some algebra to clean up this situation. So if I'm going to do that, sometimes what I like to look at is the 2x times the x to the 1/2 power. I don't quite see anything quite yet, and a lot of times I've done many of these, so I kind of know where this is headed. So I'm going to try to demonstrate it using the techniques that I think will get you with a better looking expression. Lots of different ways to approach this though. But I'm going to be looking at the x to the 1/2 times 2x. Again, if you multiply with the same base, these are monomials. You keep the base, you add the exponent. The exponent on the 2x is a 1, or the x is a 1, I should say. So that's going to leave us with 2x to the 3/2. Still got fraction exponents. Not excited about that, but we'll deal with it. I don't want to worry quite yet about multiplying everything out. I'm kind of seeing a little bit of heads up is I have a common factor in each of these. But before I go forward, I'll just keep rewriting the denominator so I don't get stuck there. And a lot of times when you're going through these, I remember I did too many of them, but we end up liking to factor out fractions when we do some of these quotient rules and product rules, just to make the expression end up looking prettier. I'm going to address this, but a lot of times if we're looking at this and we're seeing, oh, there's an x to the 1/2, and technically we do have ourselves an x to the 1/2, maybe it didn't really help to combine those. My issue is that they're not both the same. I have a negative 1/2 exponent and I have a positive 1/2 exponent as part of the 3/2. So maybe if it helps you, we're going to talk about factoring out. It's a little side lesson here. We're looking at factoring out x to the 1/2. And maybe you have some experience in pre-calc with this, but most of the time it's not very covered that much, but it just takes a little bit of brain power. So a little bit on this, factoring out 1/2 x to the 1/2. And actually, I'm going to take this with both of the numbers right here. So if we're dealing with this, I'm going to start off with trying to rewrite 1/2 x to the negative 1/2. Whenever we had to do this back when we were learning how to factor, I want to figure out how could I get 2x to the 3/2? Because I know in the first term, see if I can help with this. The first term here, that's already 1/2 x to the negative 1/2. I'm not going to have to approach this, but I'm trying to figure out what can I do to get back the 2x to the 3/2. So instead of maybe making an equal sign, I might want to say 1/2 x to the 1/2 multiplied by what is going to give me this result. Now, some of you like to work with letters first. Some of you like to work with numbers first. Totally up to you. But we can say 1/2 times what gives us 2. Half of 4 gives us 2. So sometimes that's quicker to go through. But the letter part kind of gives us an issue. This would be kind of the idea of if we're going to have to say, what do we need so that if we were to subtract off a 1/2, what do we need for this to happen? And this would be kind of similar to, let's go backwards, just even a little bit more. Try to connect this to something you kind of know already. So before I get back to this, let's try this. What if you had something like ax cubed minus 4x to the 5th? And we know the GCF is x cubed. So if we were trying to factor it out, the a part's not a big deal, but the 4x to the 5th, you're so good at this now that you already know it has to make up a 5. So this is why we need a 4x squared. So when you were first learning this, we weren't so automatic about this. So in order for us to figure out what this was, we had to say, oh, you basically subtract off what you already have, 5 minus 3, and that's the remaining exponent on the factor, or the term, I should say. So if I want to figure this out, and stay with me, we're almost done with this section. I know for sure I have to multiply it by another x. I need to open up my box again just to give myself more room. The question is the power, and it kind of is similar to what we were dealing with. What I kind of look at is if I'm trying to figure out what to write here, I would say, okay, well, I already know I need to make a 3/2. So if I have a 3/2, let's write that down. So if I have a 3/2 and I subtract off what I already know was a negative 1/2, what we end up getting, 3 minus a negative 1/2, 4 over 2, which is a 2. this should be a 2. And maybe I took a little more time to explain that. You might have been able to see that already, but sometimes some of the fractions are not so nice. So this is my technique if ever I'm thinking too hard, but I could have also said, well, I already have -1/2. How do I get to a 3/2? Oh, I need to add 2. So that will be where we're at. So play with it, let you go from there. Let's work on our factoring. So I'm going to pull out the 1/2, x to the -1/2. Now, if I do this, what I end up getting is I get this original first binomial. Nothing changed there. I'm going to subtract off, and here's where we came from this other part. I need to rewrite this, and if I'm pulling out a 1/2 x to the -1/2, I need to rewrite this as 4x squared. I know I'm okay, because if I end up remultiplying that out, I should get 2x to the 3/2. So I did have to take a little bit of time on the side to really demonstrate this. Maybe you're faster than me, and that's totally okay, but I just want to help some of you out because, you know, it's not an automatic thing factoring out negative exponents. So we'll work with that. I'm almost there. I should have still, the denominator has not changed. Let's not get lazy. Let's keep rewriting it. And now what I'm kind of noticing is I see I have 1/2 x to the -1/2 power. It's kind of a mini complex fraction here. So I could kind of adjust this a bit and say, well, I don't want fractions within fractions. Let's take that 1/2. That's really like saying 1/2. And then x to the -1/2, if I want to switch levels, I should have x to the +1/2, except I'm moving to the denominator. So this would give me 1 plus x squared minus 4x squared. I didn't need the extra parentheses anymore. And of course, the denominator has not changed. I have 1 plus x squared squared. And we can combine like terms if we need to. I have 1 minus 3x squared on the numerator now. And I'm not too excited here, but this seems like I'm able to have the simplification in this manner. And as far as I'm concerned at this point, I don't see anything prettier I could do. I would want to kind of pause and say, wait, I just did all this math. What was I supposed to do in the first place? Should I stop there? Is that the answer? Let's go back, read the directions, find the equation of the tangent line. Okay, we have a little bit more to go. So what was our purpose anyways of finding this derivative? We actually had to figure out the slope of the tangent line. I wanted to highlight that. And in order to find the slope of the tangent line, we had to find that derivative. So that's the majority of our work, by the way. Now at this point, right now we've calculated the derivative, f prime x. That's as pretty as we can make it. However, if I want to find the derivative evaluated at 1, having this 1/2 power business, it might be useful for you if you want, and we kind of spoke about this earlier. Sometimes converting these 1/2 powers to radicals could help if we're plugging numbers that are relatively nice directly in. So now, and reminding myself that is f prime x, if I'm trying to figure out the slope, that's the same thing as plugging in 1 to my derivative. So this could make my life slightly easier if I don't have myself a calculator. I'm plugging in 1 every time I see x. That's where that square root of 1 Well, I guess 1 to the 1/2 wouldn't have mattered, but you never know. They change the point of tangency. 1 plus 1 square, and again, we're squaring. So it could get quite tricky down here, even though they're just numbers. One little mistake, it throws off the entire problem. So take your time. I'm looking at this a little more carefully. Let's see, 3, 1 squared, 3 times 1. So that's 1 minus 3. 2 times square root of 1. Square root of 1 is 1. I end up having 2. 1 plus 1 square. 1 square 1. I have 2 square. We'll play around with this a little bit more. Take more steps if you need to. No problems there. 2 times 2 square is 8. 1 minus 3 is -2. And if we want to be real fancy, reduce your fraction. And that, my friends, is the slope. Now I'm pretty happy with myself there, but I want to say, am I done? Go back, read the direction one more time. Oh, they didn't want the slope of the tangent line. They want the equation of the tangent line. So now we finally have ourselves an intermediate algebra problem. Okay, so now a little bit of an intermediate algebra problem. We want to go with the equation. I'm a big fan of the point slope form. So I know my slope for sure. It's -1/4. I got to remind myself what my point of tangency is. 1/1/2. Okay, so the point is 1/1/2. So that would mean I'd be subtracting off 1/2 in this point slope form and subtracting off 1. And if we want to clean it up, a lot of times we like the slope intercept form. We just take a little more time. Distribute that 1/4. Add that 1/2 to both sides. So 1/4 plus 1/2 is 3/4. And the other point, I might be pulling out my calculator because my brain hurts, but I'm okay with 1/2 and 4s. I cook, so that kind of helps. But feel free, pull out the calculator for those. I really want you to focus on the calculus, not the what do you call it, the simplifying part. So this, my friends, is the actual answer to the problem. This is the equation of the tangent line to that curve at x equals 1. And this type of problem, it's a standard test question. Given a function, can we find the equation of a tangent line at the x value? Maybe it won't be as complicated, but this is kind of an intermediate one. There's some more ones that get quite interesting. But just kind of having the flow of how we approach this problem, something to look at. And there's always like a struggle whenever I'm going through this type of problem where I'm trying to find the equation of the tangent line. Whenever I'm trying to calculate the slope and I'm going through the generic work with the f prime x, you know, it's kind of like, how much time should I really spend simplifying? You know, is it okay to leave it like this? Whoops, I don't want to go with that one. You know, can I leave it like this step? Or should I go here? Should I go here? Is it okay to leave it up here? Or do I even bother spending my time trying to factor out that -1/2 to make it prettier? There's a lot of things to kind of consider. But I kind of work through these problems this way because in our case right now, if we're trying to plug in x equals -1 anyways, you wouldn't have to waste too much time. So if you felt comfortable with plugging in these numbers, maybe at the top step, maybe over here, then, you know, go for it. But eventually, we're going to be calculating second derivatives, third derivatives, and so on. And so sometimes it's to your benefit to try to simplify it down as much as you can, so that if you ever have to take another derivative, it's as clean as possible. So this is a time where you have to kind of discover on your own what works best for you. So I hope the problems will help you answer the question for yourselves. I will see you next section.